Yeah, so I've been working on quantum error correction for the last maybe 10 years or so. I just moved to Delft University, where we're trying to implement quantum error correction. So my focus is a bit more on practical issues. But in this talk, I hope to also inspire you that there are interesting theoretical questions here that actually relate to field theories and gauge theories. And we're actually still finishing this paper that I'll talk about, and we're actually kind of stuck. So maybe you can help us. Now, I assume that you are familiar with the Tor code. And I think the Kitev's Tor code is such a well-known object. But you may not be so familiar with another code that was proposed by Kitev, among others, Gottesman, Prescott, Kitev. That is, I refer to as the GKP code. And so my talk is about what we call in coding theory a concatenation of these codes. So what I have is I have a bunch of oscillators, so a bunch of bosonic modes. In physical systems, it could be a microwave cavity, and there's one standing wave mode, and I'd like to put photons in that mode. This is how it sort of comes out in experiment in circuit QED. And in such oscillators, I can select a subspace, a two-dimensional subspace, and I call that my qubit. And the Gottesman, the GKP code is basically a prescription for such subspace with certain nice properties. So then I've moved from an oscillator to a qubit, and now I can say I have many of those qubits, and those together are the qubits of a toric code, right? And so that's the idea. That is a toric GKP code or a surface-GKP code if the torus is cut open into a surface with boundaries. And basically the goal of what we wanted to do is understanding what is the error thresholds for such scheme. And why is this interesting is because it could be an alternative to some of the surface code work that is happening now with superconducting qubits. To make scalable, to have scalable quantum error correction. You can also ask questions, stop me. I hope to keep it, the slides are fairly informal. Okay, so this doesn't work, sorry. Okay, so here is some, my slides are a bit full, so just maybe, ignore except for what I say and just use it to pick up some math here and there. Okay, so I have just an oscillator, right? And I just have my two quadratures with the commutation relation. And so just to motivate a little bit more why this kind of code is interesting, actually 2-qubit and oscillator codes have already been realized in the lab in this setting which I refer to as circuit QED, which is microwave photons and superconducting qubits. And they have very good cavities there. So they have a very good bosonic mode, which is long-lived. And so one choice of a subspace is what's called the cat code. And it's cat as in Schrödinger cat, because the qubit in state 0 is a superposition of two coherent states. I don't know if you know what a coherent state is. It's a superposition of photon number states. N is a photon number states. And 0 is this superposition, and 1 is that superposition. And these are approximately orthogonal. That's been realized by the work by the Yale group, but there's also another little code which was recently realized. It's called the binomial code, in which my 0 is a state with 2 photons in this particular mode, and my 1 is a state with superposition of 0 and 4 photons. So again, this is an experiment in 2018. Now, I don't want to dwell onto this because I want to talk about the GKP code. There's not been any physical realization of the GKP code, but I think they are working on it. I haven't heard the latest news about this. Okay, so what is the GKP code? And I think it's a very beautiful idea. Okay, so the GKP code you have to think about a little bit more abstractly, is that you maybe are familiar with the formalism stabilizer codes, where you have a bunch of check operators, stabilizer operators, and the code space, where your information lives, is a +1 eigenspace of these check operators. And so is it for the GKP code, and the check operators are SP and SQ and powers thereof. And what is interesting is that I can make, P and Q of course don't commute, fundamental uncertainty, but SP and SQ actually do commute. And that's a really, I think, fascinating observation in the sense that if you fix the eigenvalue of SP, you don't fix the eigenvalue of P, you fix it modulo something, right? Because the eigenvalue is determined whether this is 2I times pi. And so you can actually fix not P and Q simultaneously, but P modulo something and Q modulo something. There's a common eigenstates of these. Okay, so then I can also define my, if I have a subspace, so this, it turns out to, if I say these eigenvalues have to be +1, it's a two-dimensional subspace. So I can call, I have a poly X and a poly Z in the subspace, right? Poly X just mapping 0 onto 1, and poly Z putting a phase onto 1. And these SQ and SP are just squares of this. Now, to think about this code is, so if you look at SQ, say, like I said, if the eigenvalue has to be 1, Q has to be, some integer times square root of pi, right? Because then this whole thing is I times 2 pi. So if I look at what the wave function of these states look like, so this is the wave function of 0. So this is the absolute value of Q squared, the probability. Now this is not an equal superposition, it's not an equal superposition of delta functions in Q. It's something with a Gaussian envelope, and every delta function is a little bit wider. And but you see that the peaks only occur at even multiples of square root of pi. So that's my 0. And the 1 is where the peaks occur at odd multiples of square root of pi. And the reason that, the +1 eigenstates of these two operators, they're actually not physical in the sense that they have a number of photons that is, it goes to infinity. So if we deal with this code in any finite, in a realistic system, we have to look at approximations where there's some Gaussian envelope, and in this Gaussian envelope, these delta functions have some finite width. Okay, so that's a way of representing, and that leads to errors. So there is some parameter that I can use to qualify the quality of the states, which is called a squeezing parameter, which says, to what extent am I really an eigenstate of these two unitaries? Yeah. Okay, so there's another simple way of thinking about the GKP code is also as a torus, actually. And it's a torus in phase space. So for that, I just redefine my Q and P slightly, just to get rid of these square roots of pi. It's kind of awkward. So this new Q and P obey this operation, and then you can see, what's the action of the check operators, and what's the action of the logicals, and what's the action of errors. Okay, so think about this torus as, if you go in one direction, you move in P, right? The operator P gets shifted. Now a stabilizer in this format moves, and let's say this torus has a circumference here of 2 pi, and also this is 2 pi in this phase space. And so SQ actually maps P onto P plus 4 pi, so it goes twice around the torus. And SP does that for Q, so it goes twice around the other loop, the other direction of the torus. And a logical moves around once. Right? So that makes a non-trivial loop around the handle, right? This handle or that handle. And so what the errors do, so for qubits, we have usually a Pauli error model where we say, qubits bit flip or phase flip. And so what is the role of the Paulis in this for an oscillator? It's shifts in P and Q. Okay, so I have, say, if an eigenstate of P, I can shift it to an eigenstate of p plus epsilon, and similar in q. And so that's a complete basis of errors. They're not very physical, because typically with an oscillator you'd have photon loss. You have to express it in those errors, but we won't go into that. But these types of errors, like I say, they give shifts in p and q. And then there's a clear way, there's a clear expression of when you can correct an error, which is sort of similar as if you think of, the Torah code. Also the logicals are these loops. When can you correct an error? Well, when the strength of the shift is at most sort of half a loop. Okay, so that's a little bit the sort of conceptual idea behind this code. Are there any questions here? Okay, so let me now tell you, if this talk is a little bit like, in territory that you're not so familiar with, let me now kind of summarize what I want to do with this talk, or what the results we've obtained is one thing. So the first question we asked is, I'm not doing concatenation within Torah code. I have a single oscillator in which I encode, I select this two-dimensional subspace and say I have some state in this two-dimensional space, and now I do quantum error correction. So what quantum error correction usually is I have to measure my stabilizer checks. For the Torah code, I have to measure these things, and so for the GKP code, I have to measure this SP and SQ, and I do this repeatedly. Now, I assume that the measurement of these checks is also imperfect. And then it's a question how I'm going to process this imperfect information. Okay, so this sounds like I've explained this as a sort of a very mundane task, but it turns out to come down to the evaluation of a Euclidean path integral of a particle in on the one-dimensional line. Okay, so that's the picture I try to make clear to you. So the second question is this question about scalable quantum error correction. So let me defer to that to the end of the talk. And we have also a third result, which is a bit to contrast that. And I'll just, I won't prove the theorem because it's kind of a long proof. But we have a very general no-go results for what we call continuous variable stabilizer codes. So what is this class of code? So the Torah code takes qubits and discrete errors x and z and encodes, a discrete amount of information. The torus encodes two logical qubits. There's also, for every stabilizer code, there's a continuous variable version of it. And such a continuous variable version, and these were first written down by Brownstein and Lloyd and so on, if I take the continuous variable version of the Torah code, it doesn't encode two qubits, it encodes two oscillators into, a lattice of oscillators. And so you say, well, I'm trying to, stabilize an oscillator, and it turns out you can prove that this is not working. So for the Torah code, we have this picture that if there's topological order. If I take the Torah code to be bigger and bigger, I get more and more error suppression, as if my error rates are low enough. I'm in the topological phase. For these continuous variable stabilizer codes, there's no topological phase. There's no advantage of taking a larger L. They're completely useless for protecting quantum information. And this turns out to be sort of related to this, by which there is actually the Surface-GKP code. The fact that it has a threshold is actually a much more subtle issue. And also how to decode is a much more subtle issue. And this is relevant because we use models where we say, oh, okay, we have qubits and they have, X and Z errors. But actually, if you look at superconducting qubits, they're not qubits, they're anharmonic oscillators. So we treat them as qubits, but it's an approximation. So this thing about what can we do with oscillators and can we really encode discrete amount of information in there and stabilize it and stabilize it more if we have more redundancy, is actually a subtle question. It's a question we have to be in the right part of, you know, phase space. And it's not completely, I think, solved by this Torah code picture. So that's sort of part of the work. Okay, so now, so I'm going to see, I'm not sure I'm going to cover how much I'll be able to cover in this talk, because I worry I have a bit too much. But let me just focus on the results that we have for a single GKP qubit first. Okay, so now it's going to be a little bit, so now one first has to settle with an error model. And of course everybody can do Gaussian integrals, so it's always nice to choose an error model that allows you to do Gaussian integrals. And let's look at this error model here at the bottom. I have some density matrix rho. Imagine it's the state of an oscillator. And it undergoes some shifts in P and Q, which are like this. And these shifts of strengths U and V are taken from some Gaussian distribution with standard deviation sigma 0. And that's a channel, and I call that channel N of rho. And this is the channel that we insert in a circuit. We assume that preparations of states and gates are perfect, like a C0 gate that's done here, it's perfect. And we just put the error in the channel. And that's just a modeling step, and we have arguments why that's pretty general. So what we look at is something like this. I have maybe a perfect state. It's this infinite, you know, state with infinite number of photons, the perfect eigenstate of SP and SQ of the checks. I have this channel N, which is this Gaussian shift channel or Gaussian displacement channel with standard deviation sigma 0. And then I have an error correction step of the GKP code. Now, you probably hadn't heard about GKP code, so let alone know how you do error correction for the GKP code. And the only thing I can say about it, it involves another ancilla. And this is typically how error correction is done, right? This qubit undergoes some errors. I need to get another qubit, couple it to my data qubit, and read out this qubit and learn about what errors have happened. And so I couple it, so that's a C0. I have to do this two ways because there are two types of errors. There's shifts in P, shifts in Q, which is similar as like your X errors and C errors. And then, you know, the readout of this data qubit is also imperfect. So I'll insert another noisy channel N prime, which could have a different standard deviation. And because these are oscillators, I don't measure, you know, 1 bit. I measure Q. So we assume that's a perfect measurement of Q, but there, you know, before that there were some shifts, so effectively it's a noisy measurement. Okay, so that's one round of QEC, but that actually corrects for, you know, shift errors in both quadratures, so both shifts in P and Q. But we would just like to focus on one type of shifts, like the shifts in P, because the error correction for the other shifts are the same and independent, so we ignore this. Okay, so I think I already said this. Okay, so what do we have now? So this is something where we have a repeated circuit. So I have an encoded state. This is a state I want to preserve. And every time it undergoes some noisy channel N, which is this Gaussian displacement channel, Gaussian shift channel, I couple it to a perfect data qubit, but then mess it up a little bit and measure it. And I just repeat this unit. And I repeat it some m+1 times. Now, if this measurement was perfect, meaning that n prime was the identity channel, no added noise, then what would happen is that based on this measurement, and this is why you do this C0, you would learn how, you know, what shift has happened. And so what I said before, so what do errors do on this GKP? They shift P or Q, and if the shift is less than pi, I can correct it. Basically, I shift back, you know, I say, oh, I need to shift back by, you know, at most pi, and if the actual shift was more than pi, I, you know, make a 2 pi error, which is illogical. Okay, so that's, so if this is perfect, I can use this Q. to correct my qubit, and sometimes I make a logical error, right? Sometimes I kind of move my 0 onto 1 and vice versa. But so if I do this many times, you know, the qubit will lose its state. So will there be some decay? The probability for logical error is increasing. Right? So that's when this measurement is perfect. But now when the measurement is imperfect, I should completely rely on this this information. It's much better to collect the whole, you know, the whole sequence of values of this Q that I measure, and do some Bayesian estimates. So what we do, and this is what's called maximum likelihood decoding, we'd like to say, well, given Q, which is a vector of, you know, this value, that value, and up to the n+1 value, what we'd like to do, we don't do any error correction actively, we just like to decide whether the shifts that have happened on the data, all these shifts together, whether they add up to something that's close to a logical X, so close to a 2 pi loop or not. Right? So we can say, well, it's sort of like, you know, the shifts, what they do on this data, they, you know, move you around this torus, and you have to decide, do I have close to an odd or an even winding number? Right? That's the problem. And I do that based on these Q values. Okay, so now let me rewrite this, show you how this is done. Okay, so what you have to decide is that given Q, what's the probability for no X error, meaning, you know, even multiples, you know, even windings around the torus, and the probability for an X error is an odd windings around the torus. And you can write this, so this type of probability, you can say, okay, it's the probability, you know, given X, given Q, what's the probability for a family of shifts at the first error correction step, the second, etc. So phi 0, phi 1, right? And then I integrate over all the shifts because I'm only interested in you know, knowing where the last shift lies. Okay, so with some Bayesian, you know, we just can rewrite this, and then we do a reverse Vlan approximation. Vlan approximation is something where you you know, rewrite something like this with a cosine. We can rewrite this. The upshot is really this. We can rewrite this. I omitted this thing as a like I said, a Euclidean path integral. We can interpret it as the Euclidean path integral with an action for a field, which is a one-dimensional field of these shifts. And this action has, if you think about, you know, this is sort of like a kinetic term. So there are two parameters, let me say, there are two parameters here. One is the, one is this, okay. One is this noise, which is, amounts to a standard deviation sigma, and one is the noise here, which has a standard deviation sigma m. Okay, so there are two parameters that I'm can deal with. Why is this blue now? Somehow the connection, I think, got messed up. Now it's red. Okay, nice. Okay, so the point is that what I need to do, in principle, is I need to calculate this quantity, given my Q, the experimentalist learns Q, right? Determine the difference between this and that, and if this is larger, you say, okay, no X error, and if this is larger, you say X error, and you reinterpret the, you know, if you finally measure the Q, but say, oh, I know it has been flipped, so when I find it 0, it really was 1. Okay, that's what you do with this data. But so you would have to evaluate this path integral. Okay, so now how would you do, what would be a good strategy for estimating this? Well, you probably do a minimum action, you apply a minimum action principle, right? You would say, well, maybe the path integral is dominated by the path of minimal action here. And that's just an equation of motion for this field. So now that's a continuum limit, but basically this is what we do. So we have, we say, if so instead of I can evaluate this whole path integral, but I can also do a more clever procedure, and I can see how well it does. And the clever procedure is actually fairly dumb. It's like you're having these values for Q, which is what you measure, and you are at some phi of this, at some, on this line. And then you kind of look at the next value of this phi that minimizes this function. Anyhow, so let me just show you some data. This is very hard to read. This is a bit unfortunate because I think you can't see the opposite of this. So what we compare, so this is number of rounds here. And this is how this shift value. So there's a real trajectory. These shifts go to, so the red band is where you say, logical error happens. And the green band is no logical error, right? It's this winding thing. So, so this, this is the real trajectory. It goes sort of like this. And the goal is to track, with the data you get, to track this trajectory. And so this doesn't always happen, but what we see, and unfortunately you can't see this data so well, is that this minimum action principle, which is much less computationally intensive, follows the optimal strategy, which would consist of, evaluating the whole path integral pretty well. And what is nice is that this minimal action idea here is very much in line with, for our stabilizer codes, we do something called minimum energy decoder or minimum weight decoding, and this is sort of the equivalent version here. So this is a new idea that we have formulated here. Okay, so how am I doing on time? Are there any questions here? Are people following a little bit or falling asleep or? Okay, so now let me summarize, and this is maybe again it's too small probably. This results on continuous variable codes, so let me read this out. So a continuous variable code, I have n physical oscillators, like a torque code, have n qubits on my torus. And that code, say, encodes k logical oscillators. And the way you give a continuous variable stabilizer code is by nullifiers. I'll give you an example in a moment of these nullifiers. It's just a way of describing the checks of the code. Let this code undergo independent Gaussian shifts in P and Q of variance sigma 0 squared on each of the oscillators. Okay, so each of the oscillators undergoes this Gaussian shift channels with some variance sigma 0 squared. And then it's followed by some perfect decoding step. So we measure all the nullifiers, we measure all the checks, and we infer, what error has happened, what shift has happened. And we make mistakes in doing that, and we get an effective shift channel on the encoded oscillators, right? Because these are also oscillators. So they can also have shifts in P and Q. And then you can ask, what does that error model look like? And the thing is, that error model is again a model of Gaussian shifts. But then you can ask about the standard deviation or the variance. How is that changed? And what we prove is that, and maybe it's more easily said, let's say we encode one oscillator. So then effectively there'll be logical shifts in P and Q. And what we see is that the variance in P can go down, but then the variance in Q goes up. So we call that squeezing, in the sense that I can get error suppression of shifts in P, but I pay for it with error increase for shifts in Q. And if I want to store an oscillator as a quantum thing, I need to suppress both. The goal is to suppress errors in both these both shifts. And so an example of this, so this is really, it really says these codes, well, this is a particular channel, this is the Gaussian shift channel, that's why we can analyze this. But it really says these codes are completely useless. I mean, this is how I interpret it. And this is in some sense in accordance with, yes, thank you, with there are no go results for Gaussian quantum error correction, because in this continuous variable codes, your code words, the states are actually, Gaussian. If you're familiar with Gaussian quantum information, they're all Gaussian. Your decoding step is Gaussian. So, what do you expect? We have to depart from this Gaussian. But I don't think previous results in this area don't really imply this directly. I think it's a more stronger result. So one thing about the squeezing, it can depend, like for a continuous variable torus code, it can depend on the torus has two, there's an Lx and an Ly. There are two directions, right? Lx and Ly. And it can depend on this ratio. And the nullifier, see the code that for a continuous variable torus code, the checks really are something like if you look at, usually for the torus code you have a star and a plaquette operator. Now on these links are now oscillators, right? And the nullifier is something that says, well, take the p's of these four oscillators in some combination with pluses and minus, so like P1 minus P2 minus P3 minus P4 on a code state, and that should be 0. Right? That's the constraints. And that's why it's called a nullifier, because the code state is the 0 state of these operators, these linear combinations of these checks. Okay, so now let me say the last topic. So I already announced this a little bit. So there's a lot of interest in bosonic codes. I've shown you that in the first slide in the circuit QED community. So you like to use your microwave cavity to encode a qubit. And so maybe you get a better qubit than other qubits they've obtained. But then, what's the next step? That's to say, you'd like to, for quantum computing to take off, you'd like to make qubits using error correction which have error rates which are very, very small. Right? And the Surface code is a scheme for doing this. But can you use these bosonic qubits? Now, let's say you have many oscillators. So that's this scheme here. The oscillators are in black. So this is a little box. And now I would like to have a lattice of oscillators. And each one of them has a little light blue ancilla oscillators that's used for my GKP error correction, because I use an ancilla. And at the same time, I'd like to, just like the torus code, I have star and plaquette operators by which I'd like to measure, the P's and the Q's of 4 of them. So look at least these 4 oscillators. Their P's will be measured and, using an ancilla, which is the green oscillator. Okay, so that's sort of this circuit. I have 4 oscillators. So this is how my QEC looks like. I have 4 oscillators, say, 4 out of this picture. Each of them undergoes this shift channel. I do a step of GKP quantum error correction to try to make this continuous error channel into something that is just X or Z errors, discrete bit flip errors. But because my GKP is not perfect, doesn't quite happen, then I have to do some C naughts, ignore that this looks funny, into my ancilla oscillator, which is this green one, say, and that again is a noisy measurement. So there are several parameters. There is a sigma here of the shifts on the data oscillators. There is an error in the GKP, which I call sigma m, and there's an error in this measurement, which I call sigma t, but which I'll sigma. And so there's 2 limits that you can easily study. So there's very simple limits. If sigma m goes to 0, so sigma m is the error rate on the GKP ancilla. So if this GKP error information is reliable, is perfect, I will correct the shifts to be, either, 2 pi or not 2 pi, but that's just sort of, X or Z errors. There's no continuous shifts anymore. That's when it's reliable. And then what you get is just the usual Tor code story. So there is a phase transition at a critical value of sigma and sigma t. And this maximum likelihood decoding problem that I discussed in the GKP case maps onto a random plaquette gauge model in 3D. So this is an old sort of result by Dennis et al. But now there is another limit where sigma m goes to infinity, meaning that this GKP error information is completely unreliable. I may as well not do it, because then it turns out that if you do the same, you express this maximum likelihood problem, you get a compact QED in 3 dimensions. This is a gauge model with a gauge field which is a Z2 degree of freedom. It just comes from this sort of discreteness of this error. Whereas here you have a sort of a U1 degree of freedom. And there's randomness because it's set by the measurements that you do. And there's no phase transition in this model for some critical sigma. And this is in some sense a little bit in line also with these no-goats of continuous variable. If the shifts are continuous, it's unlikely that you'll have some memory phase. And the question is what happens in between. Now I have I'd like to wrap up soon. I have 2 slides which are very technical, and I'm not sure I want to show them because they are, well, okay, no, actually I have another question, but I don't want to. There are what are these models? What are these partition functions? And it's kind of dense, so I don't want to write this too much. So in the case where the GKP error measurements are completely useless, I just have something that only depends on this Tor code, and I have something where I have a path integral over a field a mu of r in 3D, and the mu live on links on a dual lattice, and I have a something I can interpret as a partition function, but it has randomness determined by the errors, and it looks like this. I don't think I have the time to explain this so well. But then you can understand if a mu is instead of being continuous, if it's discrete, let's say it's only an even or odd multiple of 2 pi, and the errors are only even or odd multiple 2 pi, then it actually reduces to this model that Dennis et al. Wrote down for the random plaquette gauge theory in 3 dimensions. And the full model is something that was suggested. So we've actually struggled with this because it's something that looks like a gauge theory coupled with an XY model, but it's not like what's exactly studied in the literature, because it has randomness and it has a breaking of this AZ. So this AZ is a gauge field. It has 3 components, but in our model, in the Z component, it's an integer times 2 pi, so it's actually breaking to a Z2 gauge field. So what you can get out of this? Well, that it's complicated. I don't want to discuss this, and I don't think we have a story. What happens with this phase transition? Going from the discrete to the continuous case. And so let me just leave some room for questions. So we have 2 things. So what we're currently struggling with a little bit is to get. So the surface code with the discrete errors has an efficient decoder. That decoder can be used also to estimate the threshold, and that's very important. If I have a proposal and I say make a big lattice of 100 by 100, and there is no efficient way of processing the error information, then this is not a viable scheme. So I'd like to develop an efficient decoder that maybe is not perfect, doesn't perfectly solve this maximum likelihood problem, but still shows a threshold. This is the way to demonstrate a threshold. And we haven't found, we've been struggling with this because we have all these cosines, and then we can give Gaussian approximations, but then we're worried that we throw away too much. And The other thing is that what one can do, and we just haven't done this, is that this novel random plaquette gauge theory with these continuous variables, one can do a Monte Carlo simulation of this, and there's a Wilson loop loop order parameter what you can look at, and you can see whether its expectation value switches from a parameter to an area law, and that's a feasible scheme, but it doesn't give us necessarily an efficient decoder. So I think I'd like to leave it at that. No, it is pretty good, but okay. So I can tell you one thing. So we did some work with the Yale group before where they said, like, just ignore some of this, but let's say we have if you have photon loss with some rate gamma, and there is some amplification step. Well, there's some specific step that they imagine that they can actually do also an experiment. Then after this step, you map onto a Gaussian shift channel with a sigma 0, which relates to your gamma. And so this is also giving us an idea about what sigma 0 we have to be in. Now, the one thing about this shift channel is it's stochastic. It's a probability distribution. Whereas if I have an imperfect GKP state, I can write it, and Gottesman, Prescott did that, as a superposition of these shifts, but not a mixture, right? So we kind of treat everything that's a superposition of shifts, we treat as a mixture. But this type of approximation is also done for qubits, where you say, well, errors can add coherently. If I have poly bit flips, but actually I just have a state which is superposition of no error plus bit flip error this or z flip error that. So that's a reasonable assumption. But we haven't studied how, there's people studying for qubit codes how the coherence of errors changes thresholds, and we haven't engaged in that. So that's one caveat. Yeah. Well, I don't know. It's be careful. I think it is a good approximation, but I think what this work shows is that you have to be in the right regime of errors and error suppression for that approximation to be really valid in a scalable fashion. Because I think the qubits there, they worry about leakage errors, and they suffer from that also. Now, the thing is, if you encode a qubit in an oscillator, all errors in the oscillators are allowed, and none of it is leakage, and you have to deal with it right off the bat. And that's what this work sort of focuses on. What's the effect of that? And I feel that, there is sort of a phase transition where we are sufficiently in this discrete thing, and it relies on, it relies on the value of strength. And hopefully we are in that regime, right? Physically speaking, or we can engineer ourselves to be in that regime. Yeah. Okay. Yeah. Other question? Yeah, sure.